Okay, good morning all. Welcome to my session on you may also like product recommendations. So I am Ramesh Babu Lakshmanan. I am a Cellstat AI researcher. I also hold a managerial position in another organization, and I have 14 plus years of experience primarily in banking and financial domain. I'm primarily responsible for all the project program activities in my current role, and I have handled and implemented multiple projects in various methodologies. There is a bit of lag here, Vivek. Okay. Okay, so in a brief, 14 plus years of experience, and I deal with product scope financial management in the current organization. And I am passionate for runnings, having completed 2 of marathons. So I'll just quickly move into today's session, which is about recommendation systems. Vivek, are you able to see my agenda screen?
No, it says about myself.
Okay. Pardon me for some slowness.
Yes, clearly.
Yeah. Okay. So today what we are going to do is based on the purchase history, we are going to apply 2 different methods to come up with the product recommendation. One is fast text method, the other one is doc to vector method. So I will just show you in the subsequent slides how we are applying these algorithms and coming up with the recommendations. Vivek, next slide, please. I will just quickly move through. Unfortunately, we lost some time over here. Okay, so what we are seeing here is, in general, what are the recommendation approaches and what are the items in my cart. So what happened one day, I just went through my shopping cart, shopping cart where I usually apply for, purchase the online products for daily groceries. I did realize that whenever I ordered milk, I have ordered bread. Subsequently, when I ordered bread, I have ordered butter. So this can very well serve as a recommendation mechanism, or this can very well serve as an approach for me to recommend. For instance, next time whenever I order a milk, I can probably, or the system can probably recommend a bread, and whenever I order a bread, the system can recommend me a butter. So this is like a straightforward approach, right? And this is unique to me. So similar.
Hi, Ramesh. We lost your audio now.
Other features, right? We can also find out other implicit features by means of different models such as SPM, LDA, and SPD. What you see in figure 2, which is a connected network, you can see whether you are online or offline, we are always connected by some means or the others. Some people are always similar, some people may be dissimilar, some people may be similar on certain items, some people may have different opinions on different items, right? All these can serve as a data for us to do the recommendation. So we all have been connected for ages. However, the advent of the internet and the algorithms have made the product recommendations more easier, because we are now purchasing more things online. We are leaving a lot of footprints. we are giving a lot of feedback in terms of purchases. So this has been one of the hot markets right now, because every company or every retail segment is trying to actually come up with the right set of approaches to recommend to the customers. So just for instance, if you see the two characters here, right? I mean, they may have watched the same movie, they may have read the same book, or a person may be following another person in the social network. So you are what you're saying here is we all have been connected, and then we are trying to use this as a recommendation. We can probably use all those features as a recommendation mechanism. Next slide, Vivek. Okay, so as I told you earlier, today I am trying a different approach wherein we are going to use word embeddings followed by sentence embeddings to come up with recommendations. So so in general, I will just briefly explain word embeddings and sentence embeddings. So the word embeddings are not necessarily for recommendations. The original purpose is for totally different purpose, where we want to actually understand how to predict the next word, right? And this has got a lot of different applications in natural language processing in terms of text classification. So we can also use this as one of the features to come up with the recommendation. So traditionally what happened is whenever we have set of words, right, we use one hot encoding for representing those words in terms of integers. So the table you see is, for example, if I want to represent a sentence, I ate the orange for the breakfast, I can just key in some unique integers, right, and they can be encoded. So why don't we just continue to represent words like this, right? And why do we want to actually change? And why don't we want to have this kind of representation? One, it doesn't make any sense, because there is no relation that I can get by means of by means of a representation of I ate orange, right? For instance, between I and age, there is a different number, but can I use that for any computation? No, because it doesn't make any difference. Apart from the number itself is different, right? And the other thing is, if you use a lot of zeros over here, right? So in terms of storing these words, if we have a unique representation for each of the vocabulary, we may have probably millions or billions of words if you take any language. And if you want to start encoding everything, we might end up with having a lot of memory with a lot of sparse matrix, which is not really a right representation, which is computationally expensive. So to avoid all these, right, what has happened in the past few years are the word embeddings. There are various techniques which has come up to actually give in a better word meanings for embedding the words or to represent the words. Those are, some of them are count vectorizer, TF-IDF vectorizer, hashing vectorizer, word to vector, GLOVE, and fast text. And if you see, word to vector is from Google, GLOVE is from Stanford, FastText is from Facebook. So each of them has their own advantages, benefits, or certain limitations. For this purpose of embedding in this classroom, I have used FastText as a method to embed. So I will explain you briefly what FastText, how it works, and how I'm using this fast text word embedding technique to embed actually the products. Next slide, Vivek. Okay, so this is a small representation of word embeddings, how it works. So once you feed in certain words, right, let us say any sort of word embedding technique that you have seen in the previous slide, you can represent them rather than as one hot vector, you are representing them in terms of different features. For instance, living being, feline, human, gender, royalty, verb, plural, these are certain features or certain dimensions that you can represent the words for. You can actually, the machine can actually learn certain attributes for each of these words, and these can be represented in a vector dimension space. That is what you see in the boxes to the next boxes to the right. You can see that dog, cat, kitten, and houses are represented in certain vector dimension space. What you see is a two-dimensional projection. Though in reality, words will be embedded between 100 and 300 dimensions by the usage of different techniques. So what figure 4 shows you, actually you can do some vector computations, because each of the words such as king, man, queen, woman are represented by means of certain vectors, and probably If king is at a certain point in the space and man is at a certain point in the space, the distance between king and man or queen to woman probably will be same, which means that the representations are almost having certain meanings embedded with it, and you can use this for further computations. What you see in figure 5 is a 2D representation of the word embeddings, where you see that the related words such as city names, the relations, the feelings, the travels are embedded in different spaces where they are clustered together. So from a big set of vocabulary, you can actually get into this kind of a word embedding representation, which can be further used for any sort of computations. Next slide, Vivek.
I have a question here. What is the need for embedding words?
It's a good question, actually. So why do we need to embed the words? We want words to use as a features to actually make some predictions, right? Words itself do not have any meaning unless we can derive certain features out of it and then can use for certain classification techniques. For instance, certain techniques, let us say classification, right? There is a certain word, set of words you want to translate into different languages. You may want to convert a text to speech, and then you may want to summarize a text paragraph. You may want to actually find out similarity between two sentences. So in order for you to do all those computations, we have to make sure that words serve as an input from which we can actually derive some embeddings. When I say embeddings, have some establish certain semantic relationships between the words, so that use that as a starting point to do some computations, so that we arrive at what we require. For instance, whether it is classification, whether it is summarization, or whether it is similarity, right? There are so many different applications, the end results, which can do beautifully once you have a right representations for the words. And when you say right representations of the words, nothing but right meaningful embeddings of the words in the word vector space.
There's one more question here. These words are coming from where? Like shopping comments?
Whatever I show you here are certain examples of words which are actually part of any normal text corpus, right? So the source for your words can be anything. Social media, if you go, there will be a lot of different words. The reviews that you give in IMDb, the feedback that you enter for certain products. So any of these can serve as an input, and any of those can be embedded dimensionally so that you can derive some meaningful relationships. So what I'm showing here is certain example, but what we are going to do is we are actually applying the same technique to come up with the embeddings for the products that we have bought. So you can actually interchange the words with the products over here. Okay. So Vivek, I think I will. Can I send you the data set as well so that I can show them how the data set is?
Yeah, sure. You can WhatsApp me.
Okay, just a minute. Okay, I'm pinging you the Google My Drive link. Okay, so I will just continue. So what I will just brief upon what fast text method is. So fast text is one of the techniques for embedding words, in addition to so many other different techniques which are available. But what makes fast text is fast text can actually use to embed the sub-word information. So what do you mean by sub-word information, right? So you can look at figure 6, right, where instead of looking words as a single unit, fast text looks into word. Vivek, the next slide, please. Yeah, the fast text looks a word as a subword, as a set of subwords which has its own set of meanings, right? Just to give you an example, let us say if you have a word like unquestionably, right? You can actually split this into different subwords, wherein you have a proper stemming, the root word of question. Then if you add some prefix and suffix, if you combine all this and then come up to a specific word which is unquestionably. So there is only one word over here. You can split this into different words, and each of them may carry their own information, because a word can be a mixture of a lot of different words, right? So fast text looks word in that format, which is different from how word to vector or other algorithms look into. Say for example, if I feed in any set of vocabulary for a fast text algorithm, and how it derives the words, sorry, the subwords from a word is, if there is a word, for instance, where, right, and if you want to embed it in a 3-gram character, n-gram words, it will actually split into, let us say when you give n equal to 3, you can set this parameter how much ever you want in this algorithm, and then it will give you a 3-letter word, how many ever 3-letter words that are possible. It will go from, start from W, and then it go from all the words, and then it go throughout the words, all the letters, and come up with a 3-letter words. Similarly, you can set up a minimum character n-grams, or you can set up a maximum, in which case it will actually give you a lot of different combinations. That is what you see in this example of n equal to 3, n equal to 3, or n equal to 4, right? So what will happen is a single word is two different subwords, and then an embedding will happen for all these different subwords. So what will happen? You will get an embedding not only for the words, you will get embedding even for all the subwords. So literally how it helps is, for instance, you may train your vocabulary. So let us say you have a vocabulary of 1,000 words, and you train your algorithm for those 1,000 words, right? Because that is the training set that you have used. And when you go for a prediction vocabulary which you have not trained, in that case, the word to vector algorithm or other algorithms may have challenges in giving you a word, in giving you a right embedding. But what can happen by a fast text is it will give you a nice embedding, because it will split given in terms of different subwords. And if those subwords have a similar, if those subwords are already present in your corpus, it can actually take up those embeddings, and it can actually rightly match the right embeddings, because most of the times if you split the word, you may be able to match with one of the other sub embeddings which we have trained. So in this way, the out of vocabulary words can actually have a meaningful embedding if we have trained that vocabulary by means of fast text. So I think the advantage of it is clear, right? Because we have, since we are splitting into the multiple n-grams, and each of them have their own embeddings, you may not really have to worry about the out of vocabulary words. In addition, right, it follows a typical way of training. One is this continuous bag of words, or the other one is the skipgram model. The primary difference between those two are, it's the way how you predict. You give a context words as input, and you predict target word as output, or you give target words as the input, or you predict the context words. So there will be a window size based on which the context or the target word will be decided. and the prediction will happen accordingly. The prediction will happen here by means of probably a two-layer neural network in which the embeddings will be computed, and then we may use a hierarchical softmax and negative sampling. So those are the different techniques which will be used for embedding, and I would not get more of those I mean, I will not delve more into those for this session, because we are primarily focused on how we are embedding our products over here. So Vivek, how do I share the Google Colab link to you? Or I will just show you the code briefly as to how this embedding happens.
You can send in WhatsApp.
Hello? Okay.
There is a question how to choose N here.
Vivek, you got my data set and the GitHub link.
Yes.
Okay. So what you are showing here, what we are showing here, you is the data set that we have collected. It's an online retail data set which has the details of the customers who have purchased, the invoice number, the corresponding items which are purchased, the unique identifier which is shown by a stock code which is in column B, the description of the items, the quantities which are purchased, the date which is purchased, the unit price, customer ID, and the country. So the important the fields which are of importance which we are going to use as features are the customer IDs, the stock codes primarily, because we can actually figure out what are the items that customer purchased once we take each of the customer IDs and then find out the list of items they have purchased. We are also going to sequence it like how the words are sequenced, like we have to using the invoice date and time. We will be sequencing it so that we know exactly in what order the customers purchased. So if you see this, right, you can make a similarities between this and also the way how the sentences are written, right? The sentences are actually written in sequence because the context of the sentence will depend on the way how we write it in sequence, right? Similarly, for each of the customer, I'm going to take the different stocks. I'm going to basically group the stocks by the customers and in terms of sequence, so I understand exactly what order the customers have purchased. And instead of using the sentence as an embedding, I will be considering the products list here as sequence of words, and I will use this as an input to my fast text. And that in that way, it will create embeddings for all these different products. Okay. So the first few lines here are about how we are handling the data, the cleanup of the data. There is not much cleanup required except that there are certain values which are not present. You can just keep scrolling down, Vivek.
Yeah, is this fine?
So I will feed basically the list of, so what I do is I group the products by the customers. I feed that as an input. You can see in the line number 21 where I have like 3935 unique list that we have created. And and I'm going to use FastText. There is a native implementation available, but I'm just going via Gensim. So from Gensim, I'm importing the FastText model, and I'm using FastText to train the model. There's certain model parameters that I have inputted, for instance, the window size, whether it is skipgram or continuous bag of words, whether we use a hierarchical sampling, what is a negative sampling window, what are the learning rates. So once we do that, right, where can you just scroll down? So ignore the errors because I just tried to train again. So what would happen is I have tried to train the model. I have saved the model, and I have just reloaded the model. And once I reload the model, what I would get is actually what you see in the next line, which is wv.vocabulary, where you see keyed vectors which are there for each of the vocabularies. So vocabulary here translates to the products, which means that the algorithm has actually found some vector embeddings for each of these products, which we think should be a meaningful representation. Next line, Vivek, just keep scrolling down. So these are all the keyed vectors. There is a difference between the model and the keyed vectors because model will have a lot of different parameters. You can actually safely discard. That is one good thing about the word to vector, Gensim package. You can just take in the keyed vectors, which will have all the weights associated with each of the vectors, and then you can use that for making further predictions, or you can use that further for any computations. Yeah, unfortunately the vocab size is big, so you just see that there is a lot of um, vector embeddings. Okay, so so what you see here is the vocab size, and also what you see in line 41 is I have given a new product 2 to 3, which is not there present in which is not one of the items which a customer has purchased, because there is no such item. But still, because FastText used sub character embeddings, it is able to get a vector for it, right? And just scroll down, Vivek. That is what you see in line number 41. And what you see in line 42 is the full vector embedding for all the words. And FastText, actually, you have to retrieve the vectors for full word embeddings, the full product embeddings, and the subproducts by two different means. One is wv.vectors will give you the embeddings for the complete, for a full word, and vector.ngrams will give you for all the ngrams in this session. And you can also see there are like 20,378 character ngrams words that FastText has derived, whereas in terms of full word vectors, it is 3166. And what you see in the subsequent lines are the representation of those embeddings in 2-dimension, because we have embedded in 100 dimensions. This is how the products have been clustered. Uh, Whatever you see in the similar colors are probably the same set of groupings, right? And what you see in the subsequent steps are, I have just tried to create a dictionary with the stock code and the corresponding descriptions.
Now, how many dimensions are we showing in this TSNE plot?
It's a 2-dimension. The 100 dimension gets converted.
Okay. So you have 100 dimensions in data set and now shown in 2 dimensions, huh?
Correct. Yes.
Okay.
These are certain pre-processing that I have done in the next few steps, and just scroll down, Vivek. So what we will do is, since we have got the embedding now, right, we can use that embedding to actually figure out what are the related products by means of uh, the most similar function, which is an inbuilt function. So we need to feed in the product or the embedding of the product. Yeah, just keep scrolling down. So this is just dictionary built to map the product ID to corresponding description. And what you see in the in this function is similar products. This is where I am actually deriving the similar products. So we have to feed in the vector, the product or the product for which we want a similar relation, and we can actually try to get the.
Is this using internally collaborative filtering of some kind, or
You mean
FastText
the
uses
similar by
collaborative
vector
filtering?
function?
Yeah.
So what it will do is it will take a cosine similarity of.
Okay. So it does use something like collaborative filtering.
Sorry, Vivek, I could not hear that question. But
Yeah.
the
So yeah.
similarity, the
Okay.
similar products are recommended by means of a cosine similarity.
Okay.
Hello.
Yeah. Go ahead.
Okay, so what you see here is, let us say if a customer purchases a product code which is 171058, I think it is slightly, yeah, 9H, 9D, right? So in the dimension space, these are the next few products which are closest to those products. So you can probably recommend these products to the customers, right? This is how the embedding is arrived at by means of FastText. Now, if you can go back to my slide, Vivek.
Okay. So
Okay, so what I have listed down here are yeah, Vivek, sorry, you have a question.
no question.
Okay, okay. These are certain key functionalities which are already inbuilt, and the way how we can access them is what I have highlighted over here. For instance, to retrieve the vector n-grams, to retrieve the full size, full word embeddings for each of the words or products, and to get the full vocabularies. So in the subsequent slide, so here with this, right, actually we have come up to part one of our solution, which is how we are able to recommend the products, how we are able to find a similar products, and how we can use that to recommend further to a customer once he or she purchases a product. Now, right, we can also go to the next step and find out the customers who are similar by means of the product purchases, right? So now you saw only the products which are similar we are recommending. Now, why don't we go and take a step ahead and group the customers in terms of their similarity and use that as a recommendation. For instance, if customer A and customer B like similar products, probably we are thinking that customer A will be similar to customer B. And once we come up with this kind of a grouping, we can actually recommend the products to each other. Like whatever customer A buys, maybe we can recommend that to customer B. If customer B buys, we can recommend that to customer B. Customer A. So in this way, we can establish a relationship between the customers. So that is what we have done in the subsequent steps. Next slide, Vivek. For that, what we have done is we have used a sentence embedding technique. So what you see in the picture here, right? I have just given you a brief landscape of how this works. You may have to see it from the, you consider this as a sort of a pyramid and read it from down, read it from the bottom. Um, So let us say that I'm just considering it as a sentence. So how in general sentence embedding works is, let us say you have a sentence varies cat, right? So fast text can do a character embedding by means of splitting them into the subgrams. That is where you see var is getting split into WH, ER, E. These are all first, just reference examples that I have given, not necessarily the right embeddings. So I is split into I and E, cat is split into C and 8, at, and there are different embeddings for each of them, which is 100-dimension embedding. And fast text also embeds each of the words in addition to the character n-grams. That is where you see the 100 dimensions embedding, which are there in the second from the bottom pyramid step. And taking one step ahead, even the full sentence itself can be embedded by means of doc2vector, which is a technique, which is a package from Gensim again. And doc2vector, how it does is, it takes the whole sentence and it gives you, it spits out the vectors for the words as well as the sentences. When I say sentences, they call it, you can call it probably a document, you can call it a paragraph. Paragraph is most commonly used term over here. So in addition to a word vector that you are retrieving as an output of embedding, you can actually get sentence vector as well as an output of doc2vector. And how this is sentence embedding comes up is by means of, again, two different approaches within doc2vector, which is distributed memory or distributed bag of words. As I said, there are again different techniques to embed the sentence as such. Those are TF-IDF, doc2vector, infercent, sentence BERT. In addition to that, there are other different techniques as well. And here I am going to use doc2vector as a technique to embed the sentences. So now you have to understand one thing here. Here sentences mean customers, right? Because we grouped by customers, and then we listed the products in terms of customers. So each of the products actually represents the unique customer list. And if we embed each of them as a whole, right, and if you get an embedding for each of the customer, each of those sentences, which means you are actually embedding the customers themselves, and you can actually figure out the similar customers by using same functions such as most_similar or anything which is available with the doc2vector. So what you see in figure 8 is one of the approaches that we have used to come up with this sentence embedding, right? So the difference, in terms of training, it is more or less similar to word2vector. If you are already aware of word2vector, you use one of the words as context and use other as a target and predict the same, right? Predict and use the training network to predict the words. Now, in addition to that, what we are also giving as an input is a unique paragraph ID, which is a representation of those sentences. So that comes in the form of a tagged document, which is fed as an input to the doc2vector. So Vivek, if you can go to my program again.
Yeah, quick question here. Do you think more recent algos like BERT embedding, Elmo and Globe will outperform, let's say, doc2vec or TF-IDF or even fast text?
Fast text testing, if you are talking about advantage of fast text, right, definitely fast text has a lot of advantages in terms of getting you a right embedding for your sub characters. Though probably in English language, I believe we may not have, we may not be having a lot of different sub embeddings, but in terms of other morphologically rich languages such as European languages, there are a lot of different sub embeddings which can have different meanings, and fast text plays a significant or good role over there in terms of making right predictions. But in terms of other techniques such as Elmo and all, right, unfortunately at this point I am not actually aware of those techniques. So I would rather limit it to between word to vector and fast text. Fast text brings this kind of advantage by means of giving a right embedding for your subwords. Okay, just scroll down, Vivek, a little. Okay, so what you see here in the subsequent steps are I am actually importing the doc2vector from Gensim, and the input for doc2vector is actually a tagged document, right? When I say tagged document, it is nothing but you are representing the sentences as a unique one, and you are actually tagging the sentences. So for tagging the sentences, I am just passing a unique ID to each of those sentences to represent that the specific sentence is unique and different from others. Just this will help the system to understand that limitation or the sequence of the words and how much a sentence is composed of. Right, a sentence should be composed of only certain number of limited words, and those can be identified by means of tags. So what would happen, right, once you feed in this tagged document as an input to the model will learn embeddings or the vectors for words as well as tags. So doc2vector gives you an option to actually not train your words, because the primary purpose of this is to actually give you the embeddings for the sentences. But here we are actually training words as well as sentences to give some meaningful embeddings for the sentences. So if you just scroll down, Vivek, so if in line number 42, I have converted the input in the form of tagged document. And I'm just showing you here one of the tagged documents, which is the second tagged document, wherein we have tagged all the words with the tag, right? So what this tag means is the tag 2 represents, it's a second sentence which is unique to these specific words. So you can you can think of this embedding in a different way. For instance, the context information, right? I'll just give you a very simple example. Let us say you are in India, right? And if somebody tells you, okay, so what did you somebody gives you a sentence, I ate dash for a breakfast, right? So probably some of the options could be idli, dosa, upma, right? Because we are in India, probably, right? Now the same sentence, if you travel to US, right? Let's say imagine you are in US or European countries, and if you are, I'm giving you the same sentence, right? I ate dash for your breakfast. So you may not be able to tell idli, dosa, right? Even though the sentence, even though you can still make, but it is not context. It doesn't make sense for the context or the location that we are staying in, because you may be eating burger or apple pie or what sort of breakfast items are available over there. So this specific context or some information related to all the words itself is missing if you see, if you take into account the word embeddings, right? Because those look into only the words, but what is the relation, what is the one thing which is common for all the words? That particular context information is actually being fed into doc2vector, and that is being fed by means of this tag. So you can say that the missing context information in the word embeddings are actually getting added by means of tags over here, and this is being fed as an input to your paragraph embedding, which is a doc2vector embedding. Next lines, Vivek. Okay. So the next few lines are about how I am training the model and what are the, so pretty much if you are aware of word to vector and the way how you train the word embeddings, it is 90% similar, with the exception that you may have to pass the tags. Scroll next line, go to the next slide of lines, right? Okay, so what I have done is yeah, just little, just scroll little up. Okay, so again, you can access the vectors for the words. You can access the vectors for your sentences or the paragraph by means of the same function, that is wv.vectors. Right, it will give you the complete embedding for your words. So still the doc2word vector model will also spit out embedding for your words and paragraphs, and you will be able to access those by means of the functions, which is that wv.vectors. wv.vectors will actually give you the embeddings for all your words, and if you want to access the vectors for your paragraphs, you can actually use another function, which is doc vector followed by tag, which will be there in the subsequent lines. So next few lines, I'm showing you the embeddings for this doc2vector output. Again, I'm showing you the 100-dimensional embedding, which we have done, which we have created, is projected in the 2-dimensional over here. Okay, and what you see in line number 18, right? Just scroll down, Vivek, a little. Yeah, so what you see in line number 18 is how I am accessing the paragraph vector, the sentence vector, or in this context, the customer vector, is by by actually using the same tag, right? This tag is specific to the second customer, which is the number 2. Similarly, for all the customers, you will be having a specific vector, which is a 100-dimensional vector that we got out of doc2vectors. Okay, can you guys go back to my slide, Vivek? Okay, now, so what we have done is, starting from the character embedding to the word embedding to the sentence embedding by means of doc2vector, we have got these embeddings, and there are certain functionals which we can use in doc2vector model to access important things, such as if you want to access the complete model, you use the model name. If you want to access the embeddings for the words, you use .wv.vectors. If you want to access the vectors for your paragraphs, you use doc vectors given the tag, and if you want to find a similar sentences, right, or in this context similar customers, you use most under similar function. What it does is, it goes in, takes in the vector as an input, or a specific tag as an input, the vector representation of the tag, and then gives you a corresponding or similar vectors or similar users by means of cosine similarity. And doc underscore model underscore infer underscore vector. So doc model, the model dot infer vector underscore vector actually constructs a vector once you key in the specific words. So this is more or less like constructing a vector based on the embeddings which is that has done. So if you can go back to my code, Vivek.
There are some questions here. Let me ask
So now
you the
in line
question.
number 20, what I have done is, I have taken a sample, the input customer 1. Sure.
In this context where stock codes are being used, is a subword embedding still useful?
Sorry, Vivek, what is the question? The subword embedding?
When we use stock codes, do we still need subword embedding?
Okay, so if I understand the question correctly, for document to vector model, are we using subwording embedding? Is it? Actually, in this context, we aren't using any subword embeddings over here, because doc to vector works similar to the word to vectors, wherein it gives you the vectors for your words, the complete words, and the paragraphs as such. So the subwording embeddings are not used over here.
Another question is also, isn't customer ID is tag here instead of index?
customer ID. So what we wanted to represent is unique. I mean, what we wanted to represent here is to give an unique ID for each of the customers, right? So you can actually feed in any unique values if you think they can make a meaningful differentiation between the sentences. You can use that as an tag. So I just used integers, unique integers mapped to the different customer product list, because each of the product list is a representation of a customer, and that's why I used some unique index or integers for each of this product list, and that is used as a tag. So what we need to have is just to show a differentiation that these are the different items over here, and how that can be used as how that can be embedded in the doc2vector model. So you can pass a different set of combinations also as tags, not only the customer IDs, probably customer interests as well. So if you use those also, so you can actually find a different embeddings if you I mean different set of embeddings, and you can do a meaningful recommendation based on those embeddings as well. So in line number 22, what I have done is I have just fed in the one of the tags or one of the customers as an input by means of most under similar function, and the tag or the vectors which have come as an output of doc vectors. Once I fed in, right, you can see by means of cosine similarity the output. Since I am getting in all the values, the topmost one is the same vector itself, because when it does a dot product, it returns you the same vector because that is the closest one. That is why you see a value of 1.0, because both are similar, and you see the different customer IDs with different cosine similarity, 0.95, 0.94, 0.9494. I have displayed top 5 customers. So which means that customer 2368 935 2992 124, based on the purchase history, right, they are similar to customer 1. So in a way you can actually figure out top 5, top 6, top 10, up to how much ever you want for each of those customers, and you can find that since these are the similar customers, you can probably recommend the products which they have bought. Let us say the products that customer 1 has bought to customer 2368, and the customers 2368 has bought to 935 or 1. So probably you can do a recommendation in that format, which will most probably suit the taste of the customers, because more or less this customer seems to have a same taste or same likings. So in this way we have achieved the second part of our solution, wherein grouping the users based on the items they have bought, and can use that also as a feature to recommend the products. Now if you can go back to my slide, Vivek. Okay, the next slide, Vivek. Okay. So what you see here is a complete the recommendation system from the start of the purchase history to how we have come up with the recommendations. So this is just a pictorial representation of how I have come up with the embeddings or the recommendations. One is you have a retail data set where you have the customer details, the items they have purchased, the sequence how they have purchased. And what we have applied here is two different algorithms. One is fast text embedding, other one is doc2vector embedding. So what we have achieved by means of this, once by means of fast text embedding, you get subword, which are the character embeddings, and you get a word embeddings, and though both reflect the product embeddings, and using product embeddings you can actually find out the similar products, and you can use that as a sort of a recommendation. And if you see the left side flow, which is document to vector embedding, document to vector embedding actually spits out the embeddings for your document ID, which is nothing but a customer and the product embeddings, which is nothing but word embeddings, is nothing but the product embeddings. And using this feature, you can actually group the similar users and can recommend the product to similar users. So with this kind of a recommendation, right, you can uh, actually recommend the right products to the right user, because one, you have found out the similar products are next. Number two, you have actually found out the similar users, and using both of them, you can actually do a recommendation that would more probably be a right set of recommendations. So this is the entire model about recommendations and how the recommendations are done via embeddings. Now, if you go back to my code, right, Vivek, okay. So what I'm showing you here is just if you can just scroll up a little, Vivek. Okay, line number 24, let us say a new customer walks in and the customer has bought these two products, right, 85116 and 21171 product IDs, right? And what you can do here is using this method, right? You can actually, using the infer underscore vector function, we can actually get an embedding the vector for this product combination, right? Because it will be treated more or less like a unique sentence, and then it can be taken as an input to create a vector. And with this vector, you can actually figure out whether to whom this customer is mostly related to, which is what is there in the line number 26. And if you see that, it seems that the customer is related to 3531, 2641. Those are the top 5 customers. Right, so now you can see the advantage, like even if there is a new customer and if the new customer buys in certain items, you can actually go back and recommend the items, different set of items to these customers, because you have similar users who are already in your database. So in this way, actually you are able to recommend the items, or you can make product recommend to the product recommends to the customers just by means of a single product purchase, even though you have not trained them, or even though you have not made even though you have not used any of them in your training data set. The other thing is, I just tried a combination which is not at all there in the data set, right? That means there is no such item, and then I just created a new item and then try to use the infer underscore vector that gives you a vector representation of that item, and I just try to find a similarity. It still gives me some sort of a similarity, right, based on the embedding, but it has a weak similarity because the cosine distance, if you see, is only 0.31, 0.26, 0.24, and it still gives me some sort of feedback that this customer may be related to the different customers. All right, and they can still use it. So whether a customer buys in a new product, or whether a customer buys in an existing product, there is still a way to use this as a recommendation system to recommend the products to the customers. By this means, you can actually establish some sort of relationship among the users, the customers and the products, and we are using that as a product recommendations. So the complete code is there in my GitHub link. Vivek, are you able to hear me?
Yeah. So audience, any further questions? Ramesh, any other
Vivek?
comments? Are we done?
Yes, Vivek, yes, yeah. So unfortunately, I'm sorry for all the troubles that we have to go through today. It's a poor network from my end. But I hope you guys are able to understand as to how, I mean, how a product recommendation can be done by means of word embeddings as well, right? And this can be one of the techniques that can be used or fine-tuned further to make good product recommendations.
Okay, sounds great. Audience, any questions? There was one appreciation comment. They liked the content a lot.
Thank you.
Any other final questions, audience? Now there is one thing here. If a new customer has never bought before, how do you deal with that?
Actually, the assumption here is if first thing is customer buys, next thing is customer, even if he doesn't leave a feedback, you make an assumption that if he buys it, he likes it. So we are using that
No,
as
let's
a.
say it's a brand new customer.
If it's a brand new customer, Vivek, if he doesn't make any purchase product, we may not be able to figure out like what to recommend unless
But don't we
he.
do like user collaborative filtering, user comparison? We check the characteristics of the user, let's say age profile, gender, with other users who are of similar characteristic, right? That's called user-based collaborative filtering.
Correct. No, what I'm saying is, yes, there is a technique to make that. For instance, if there is a content which customer likes, there are similar contents which are available, right? And if there is a brand new customer, if he is connected to some other person whom we are aware of, and if that person likes that, maybe we can recommend that product. But what I'm saying is, in the current embedding model, which I have used, I primarily have used product history of the customers as an input. So if a customer buys, then I will get an feature that he likes it and start making a recommendation. But at least one product has to be bought. But for the question where if there is a brand new customer, we can still make recommendations by means of collaborative filtering or other means, networking means.
Yes. So this presentation was about a historical customer, existing customers. When it comes to a new customer, you can always compare customer traits. And let's say Vivek Singhal, similar to Ramesh. So then I'm likely to buy the same products which Ramesh buys because my age is matching, gender is matching, and maybe other location is matching. So that is called customer based collaborative filtering. So there are techniques like that. Now, Ramesh, people are asking for data set. In the GitHub, the data set is not there, I believe.
Yeah. Data set is not there. Yeah, I will upload it, Vivek.
Okay, sounds good. So lots of good comments are coming on the comments channel. Audience, any other questions? So thanks Ramesh for an excellent session, and thank you audience for engaging and all your intuitive questions. And with that, we'll see you in our future webinars. Thank you all.